Entropy is given the symbol capital S, and it is a numerical value or measure of the randomness of an object or a system. You're going to do a lab this quarter where you will measure the entropy of a solution, and you can't actually just straight up measure the entropy of something in itself. It's not a directly measurable quantity because we don't have a tool for measuring the randomness, but you can calculate the entropy of a system by measuring other properties, and that's what you'll learn how to do in lab. The value of entropy is always greater than 0. It's always a positive number. Remember from section 18.1, the laws of thermodynamics stated that if the entropy was equal to 0, that would mean that the system had perfect order. And that is only going to take place at 0 Kelvin. So that's just a theoretical condition, to have the entropy equal to 0. Now, the change in entropy, the delta S, that can be a positive number or a negative number, or it can be equal to 0. The change in itself. So delta S is the symbol for the change in entropy for a process or a reaction. And just like any other delta, like a delta H or a delta T, the change in entropy is calculated by taking the entropy of the system at the end of the reaction, and from that subtracting the initial entropy. The values of entropy are tabulated in the appendix in the back of your book, so you will calculate it just the same way you would calculate a delta H. Really simple calculations. And again, the value of delta S can be positive if the process increases in randomness, or if the process if the products are more disordered than the reactants. It can be negative if the chemical reaction produces some sort of order in a system and the entropy decreases, or if the products are more ordered than the reactants. Or it can be 0 if the randomness is the same at the beginning and the end. Positive delta S means that the system became more disordered or random. A negative delta S means that the system became more ordered, the entropy or the randomness decreased. And if the change in entropy is 0, this means that the system's randomness is unchanged. Some examples of processes. Before I move on, I want to go back. sometimes it's a little bit confusing because we have that law of thermodynamics that says that the entropy of the universe is always increasing, that the universe is always becoming more disordered. So sometimes people get a little bit confused about the negative delta S and the delta S equals 0, and they wonder if that's a violation of the laws of thermodynamics, and it's not. That law of thermodynamics is for the whole entire universe, and this is just for an individual system. So you can have a system that is becoming more ordered, but in the process of that, the universe, the whole entire universe, is becoming more random, more disordered, and same with this down here. And in later, possibly in the next section, 18.4, we are going to, in the next section, we're going to look at the relationship between the delta S of the system and the delta S of the whole entire universe and see the big picture of it. I want to give you some examples of chemical reactions or processes that increase entropy. I want you to be able to look at, just like with the spontaneous processes in section 18.2, I want you to be able to look at processes and be able to predict the sign of delta S for the reaction, whether or not it's going to be 0. And again, you just want to think about the disorderedness, the disorder or the order or the randomness of the system. So, for example, if you have a phase change going from a solid to a liquid, melting, or going from a liquid to a gas, vaporizing, both of those phase changes increase the entropy of the system. Liquids are more random than solids. Remember, solids have that structured, ordered lattice that they have to be in. The molecules are locked in step, locked in position. They can't move other than just vibrate, whereas liquids are free to move around. So a liquid is more random or more disordered because there isn't a pattern that the molecules take while they're in the liquid state. The gas phase is even more disordered because the molecules aren't even in contact with each other, so there's even less of a pattern in the gas phase than in the liquid phase. So when you go from a solid to a liquid, or when you go from a liquid to the gas, the system becomes more random, so that increases entropy just all the time. Something like combustion, where you are burning some sort of fuel, like let's say propane, with oxygen, which is a gas. We'll say the propane is a gas. And you make CO2 and H2O. And if we wanted to balance this, we need a couple of CO2s. We need 4 waters and 1, 2, 3, 4, 5, 6, 7, 8, 4 of these. So in this particular reaction, we go from 5 total gas phase molecules up to 6, so that's becoming more disordered. Combustion reactions always have the result of increasing the entropy. Dissociation process always leads to an increase in disorder. Let's say we have some sodium chloride solid and we dissolve it in water. We end up with a couple of ions, and this is increasing the randomness in part because you start with one substance and you end with 2 particles, and also in part because you start with a solid substance that has a lattice, that has some sort of order to it, and you end up with these solutions that are just the solution that's just free-floating particles without the randomness. The units, without the order. The units of entropy are joules per mole Kelvin. The whole mole Kelvin thing are in the denominator, so it's joules over moles times Kelvin. And we have standard entropy, which is the entropy that is measured at standard conditions, 25 degrees C and 1 ATM.